Vector equations. Let's remind ourselves what a vector is. Let's say we have some coordinate system here. We typically think of a vector as being a directed line segment, like so. It has its tail here and its head right here, and goes from a point to some other point. And let's say that point right here was 3, 2. Then what we probably would have done is something like this. The vector v is 3, 2, or you might have written it at some point as 3, 2. Perfectly fine. And we use this a lot in physics to show there's some kind of object moving or momentum or wherever you want it to be that has some kind of direction associated to it, direction here being relative to the x-axis, and some kind of magnitude, which is the length of the actual vector. Let's abstract this to the greatest possible extent. So a matrix with a single column is called a column vector. We'll usually write a vector as a lowercase bold letter v. So on the previous slide, when I wrote v equals 3, 2, I was writing a column vector, and I think it should be clear why it's called a column, because it's a column from a matrix, whereas I could have done this, and that would have been a row vector. I will not be using bold letters as I write, because, well, obviously I can't easily write with bold, so I will put little harpoons on top of these things, and harpoons look pretty awesome anyways, so yeah, we're going to use harpoons. Now with this new abstraction of a vector, we can do almost too many things. Alright, so let's just go through this checklist. Vector equality. When are two vectors equal? Alright, well, a moment's reflection should give you the answer to that. Two vectors are equal when exactly all of their entries are equal. So let's say I have the vector v1, which is 1, 2, 3, and the vector v2, which is the vector 1, 2, 3, the vector v3, which is the vector 1, negative 2, 3, and the vector v4, which is the vector 1, 2. Now the question I ask is, of these four vectors, which ones are equal? Well, v1 and v2 are equal because all of their entries are equal. v1 nor v2 equal v3 because they differ by that one entry being a negative 2. And notice that v4 does not equal v1 or v2 despite all of its entries being identical. Now when I say all entries, I mean every single entry in the assumption that the vectors have the same dimension. So this vector has 3 entries, this one only has 2, so they cannot be equal. Next up, the 0 vector. Well, the 0 vector is nothing more than, well, a vector made of zeros. And we'll write it like that, a 0 with a harpoon on top. Now, if you think about it, that's going to be extremely ambiguous because if I'm in one dimension, well, that's just 0. If I'm in 2 dimensions, that's 2 zeros. If I'm in 3 dimensions, that's 3 zeros, and I could do this all day. So just work under the assumption that it will be clear from the context which 0 vector I'm referencing. So don't sweat that. Next up, the sum and difference of vectors. All right, well, I just so happen to have 3 vectors already written here. How about I add and subtract them? All right, so v1 plus v2, if I were to add these, well, I'd do it in the most naive way possible. I'd say 1, 2, 3. Actually, let's change that to a v3. Plus 1, negative 2, 3. Well, the most naive way thing would just add them up entry-wise. So this would be 1 plus 1, 2 plus -2, and 3 plus positive 3. And so that's 2, 0, 6. If I were to do their difference, say V1 minus V2, well, that is 1, 2, 3 minus the quantity 1, 2, 3. Well, that's 1 minus 1, 2 minus 2, and 3 minus 3, which is 0, 0, 0. I think we all could also notice that this is the 0 vector. It's a nice little way of writing that. Scalar multiples. Now, a fun thing I can do with a vector is the following. So given a vector v in Rn, so I'm saying this is an n-dimensional vector, and some scalar r, so some is a real number, I can form alpha v. Well, how do you think you would do that? So v, being an Rn, could be written as some v1, v2, up to some vn. Well, what would alpha, some real number, times all these entries be? Well, I think the most sensible thing we could do would be is to bring it inside to all of the entries. So that'd be alpha v1, alpha v2, all the way up to alpha vn. The next thing on our checklist is some basic algebra. So let's say I have a vector v in Rn. I can form negative v. How can I form negative v? Well, I'm using nothing more than what I did right here. Negative v is equal to -1 times v. So this is the opposite vector. This is the opposite vector. And so it follows that if I form v plus negative v, I get the 0 vector. A similar thing, let's say I have two scalars. And I say, all right, take this vector v and hit it with that scalar. And the result of that, this thing right here I've underlined, notice that's a vector itself, I hit that with an alpha. Well, what's it the same thing as? Well, it's the same thing as alpha beta v. Now I challenge you all to pause here and actually sit down and prove both of these identities. It won't take much. My hint to you is just go back to the definition of what a vector v is in terms of its components. Okay, now if this seems like a bunch of abstract nonsense to you, well, maybe it should, because we haven't really tied it to any kind of geometry. And tying something in mathematics to geometry is what makes it real. All right, so let's actually do that. I'm going to do all this first, R2, because, well, it's a whole lot easier. Okay, so let's talk about sums of vectors. I have a vector v, and I have some vector w. What is the sum of those vectors? Well, what you can do is if you break it down, the actual sum v plus w can be seen as the following. Take either one of the vectors and take its tail and put it to the head of the other one. So this w here, I'm going to translate it in a parallel fashion. So that is w. Now if I draw a new vector from the tail of my first one to the head of my second one, that is actually the vector v plus w. Chances are you don't believe me. So let's actually work it out for a nice example. Let's say v is the vector, I don't know, 2, 1, and w is the vector 1, -2. So let's see if I can neatly draw this. All right, so V is 2, 1, so it looks like that. W is 1, negative 2, so it looks like that. Now if I take W here and move it so that its tail is the head of V, that's just going to translate it this way, like so. So that's W now. And then this bad boy here will be the resultant. So that's what I'm claiming to be V plus W. That looks to me to be about 1, negative 2 by my really bad drawing. Let's actually add these up physically and see what happens. All right, so 2 plus 1 is 3, and 1 plus negative 2 is negative 1. This is nothing like what it should look like. And I just figured out why. Because I'm an idiot. This vector W here is written as negative 1, negative 2. And I've written here 1, negative 2. Spectacular. So I think we just need to stick a negative there. And let's forget that ever happened right there. And 2 minus 1 is 1, and 1 minus 2 is negative 1. And 1, negative 1's right here. That's pretty darn close to what I've drawn here. Boy, I've really convinced you of this, haven't I? Excellent. All right. Now, the next thing on our list that we should really see geometrically is the scalar multiples. All right. So if I take the vector V and hit it with some kind of scalar, what's the result? Well, what it does is it takes the vector V here and it dilates it or contracts it by that factor alpha. So if I have V here and I want to form 2V, well, it's going to be the same vector but twice as long. So I go up by that portion, go up by that portion, and so this is 2V. Now we can see this a little bit easier if we just rely back on what happened here. 2V can be seen as V plus V. Well, using what I've described here, I take my vector V and put the tail of it at the head of it, so I get that. Well, it's in the same direction, exactly in the same direction, and what's the length of it going to be? It's going to be twice as long. It's 2V. So that's kind of a justification for you. And then negative V, this has a very special meaning. What it does is it negates all of the entries of V. Well, what that really does for us is it takes the vector V, it preserves its magnitude, but it exactly reverses its direction. So this is the vector V in the opposite direction. Now in dimension 2, it's pretty clear what we mean by opposite. When you get into dimension 3, it still, I think, is clear, but it's just harder to visualize, I think. So there is, say, W. Well, that means you should be collinear, negative W. So the angle between W and negative W is going to be 180, in other words. Now, there's one last thing we should discuss here, and that is this relation I asked you all to verify. V plus negative V is the zero vector. Okay? Using what we've learned, this should be easy to see geometrically. How? Well, what I'm doing is I'm setting off in some direction V. And then what I do here is go backwards along V. Okay, so there's negative V. Now how do I add vectors geometrically? I just line up head to tail. So this tail will go here, and its head, being the same length, will go like this. So I go V and then back. Well, that puts me right back here at the origin, the zero vector. Let's get some more practice with this. Let's say I have a vector V here, and I go off in some direction W. that right there is the vector v plus w. Now the question that I want to pose to you is this. Say I have the vector v and the vector w. What is that vector? The easiest way of seeing this, I think, is to give this some kind of name. Let's give it the name C. All right, so we're trying to determine a formula for C in terms of V and W. Okay, well, we know that V plus C, being a vector sum, must be W. So in other words, V plus C equals W. Well, solving for C here tells me that C is then W minus V. Now, why am I doing this? Well, behold. This wonderful theorem is one you probably remember from your geometry class. If you don't remember, allow me to refresh you. Let's say we have some arbitrary triangle. And using what we know now, we could say this vector v here and this vector w here completely determine our triangle. So I'm viewing this side and that side, and then using what we learned in the last slide, if I view this as being an arrow like so, this is the vector w minus v. And what this theorem says is the following. If I take the midpoint of this side and the midpoint of that side and join those midpoints with a segment, that green segment there, the mid segment, it is half the length of v and it's parallel to v. So if I call this vector, say, p, what I'm claiming is p is 1/2 the length of v and p is parallel to v. All right. This is actually extremely easy to prove using what we know about vectors right now. Here's how we're going to do it. Let me switch to yellow. There we go. All right. So what I want to do is take this green vector and write it as a vector sum. All right. Let's say I start right here. My path I'm going to take will be there, then along the base, and then up along that side. So if I follow these three segments, these three vectors I've resolved, I should get the green one. So in other words, my vector p here, well, it better be this vector here. Well, what is this vector? Well, it's going opposite of what w is going, so it's the negative of it, and it's exactly half the length because the midpoint property here. So that first component is -1/2 of w. This base here I travel along, well, that's nothing more than v. And this next portion, this is in the actual same direction as w minus v, but it only goes half the way up it. So that's plus 1/2 of w minus v. Well, this side is nothing more than some arithmetic in my mind. So I have -1/2 of w plus this 1/2 of w. Those cancel. Then I have v plus a -1/2 v, which is exactly 1/2 v. The conclusion I then draw is p is 1/2 of v. So I have that first portion. Now you're probably wondering, how do I get the parallel part? Well, let's go back to our discussion of what it means to be a scalar multiple. A scalar multiple is the same vector in terms of direction, but just a change in its length. So p is going in the same direction as v, but it simply is half of its length. So if they're in the same direction, that means they are parallel. So that is a pretty sweet application of vectors. If you're feeling extra spunky, I challenge you to use this to prove that the medians of a triangle cut each other in a 2-to-1 ratio. It's not that bad of a proof, and you should be able to pull it off from this. Go from here with a mid-segment theorem, going back over here, this p vector, is there some sum of wv and w minus v that will get me to p? Well, yeah, absolutely there is. It's the negative 1/2 of w, the 1 of v, and the 1/2 of w minus v that got me to p. Let's now learn how to convert a given linear system, as so, into a vector equation. Okay, so what we do here is we break it down by the variables, and then the right-hand side. In this first column, I'm visualizing, I have a 0x1 hidden here. I have a 1, a 2, and a 0. And then that's times some quantity x1. The next one I have 0, 2, 1, x2, and then finally I have negative 3, 9, 5, x3 equals 8, 7, negative 2. Okay. You're now wondering how the blazes do here, converting a linear system into a vector equation. How is this even remotely related? Okay, well, let's think about this. Before you'd ever taken this class, if I asked you to solve this system, you'd be trying to find some value x1, x2, x3, some vector, or some point, however you want to visualize it, that satisfies all three of these equations. Let me turn that on its head. This vector here, the right-hand side, let's just call it B for now, I'm asking, is there some sum of these three vectors that will get me there? Okay, in other words, what I have is 3 dimensions now. Some vector, say sitting here, this is my B, and I'm saying if I were to draw these three vectors in the 3 space here, would some of them, where x1, x2, and x3 are scalars, get me to B? In that same way, I need to find x1, x2, and x3, so that when I take this sum, I will get that particular vector. So this is the more mature way of actually thinking about solving a system. What we're asking is there a linear combination? Is there, well, I'm using terminology we don't know yet. Is there a linear sum of these vectors that will get me here? Now I kind of blew it to this, which is going back to solving that particular system. Linear combination. All right, so suppose V1 through Vk, I just grab a bunch of vectors from Rn and some scalars. Now what I do here is I take those vectors and scalars and I just add them up. That result is some vector V. It is a linear combination of these vectors, and we visualize these scalars, alpha I, as weights. All right, and allow me to phrase this poorly. Think of a position in space. Okay, I'll do it in 2 space. So there we go. This particular vector, or this point, I can view a vector as a point or an actual direction with some magnitude. This is a linear combination of some other vectors if I can basically plot a route to this point. So what I'm saying is, say I'm giving you that vector alone, and this is where I want to get, and this is all I have. Well, is it possible for me to add this vector up, this one alone, and get to v? Well, gosh no, it's in the wrong direction. There's no way for me to change the direction because scalar multiples only change the actual magnitude or the opposite direction. What I would need is another vector. All right, let's say I took this guy here. Now it's probably not very easy to visualize, and let's call this one C. Is there some linear combination of W and C that'll get me to V? Well, it turns out there will be. There's no way for me to really say what it is without actual numbers on these, but there is a way of doing it, and it all goes back. Now what I want you to do here is give me a vector that is not a linear combination of other vectors. All right, well, you can do this in a really silly way by taking this vector to be v, let's say it's 1, 2, and not a linear combination of others. Well, how about negative 1, 2? Well, this vector is not a linear combination of this one. Well, if it was, then there'd be some multiple of that one. And that's not the case because signs are different. Now, what I really want here is the collection of vectors over here to be of cardinality greater than 1. So what I can do is take a constant multiple of W. So let's call that vector P, and let's say it's negative 2, 4. V will never be a linear combination of W and P. And at this point, you're probably thinking, well, that was cheap because P is just a multiple of W, and you forbid me from using W alone. And, well, this is cheap. So let's think of another one. Let's see here. I like this one. Let's take our vector to be 1, 1, 1 in 3 space. I need this to not be a linear combination of a collection of other vectors. Well, what if I take W to equal 1, 0, 0, and P to equal 0, 1, 0? V will never be a linear combination of W and P. Well, to see why, well, let's look at that. Let's suppose it is. So that means there are two constants, let's call them alpha and beta, such that alpha W plus beta P equals V. So let's restate this. If V is a linear combination of W and P, then there must be constants, alpha and beta, that when I hit W and P with them, I get to V. All right, well, let's form alpha W. Alpha W is alpha 0, 0. Beta P is 0, beta 0. And V is 1, 1, 1. That's a vector sum. I can do that. That's alpha, beta, and 0. And that must equal 1, 1, 1. Well, by the definition of vector equality, if two vectors are equal, each of their components must be equal. Well, that forces alpha to be 1, beta to be 1, and 0 to be 1. That's no good. And so there can never exist constants alpha and beta that will take me from W and P to V. All right, now I want a vector that is a linear combination of others. Well, that's pretty easy to do. Let's go back to my example I just used, 1, 1, 1. What you should notice from this example, why it didn't work, was we needed another vector, or we could have modified W or P. What I want to do here is incorporate another vector. So W was 1, 0, 0. P was 0, 1, 0. Let's take U to be 0, 0, 1. Well, W, P, and U are a linear combination that will form V, because W plus P plus U equals V. I challenge you to come up with examples of each of these that are perhaps a little bit less trivial than these examples I've given. Let's look at this example. I ask, is this vector a linear combination of these other two? Now before I jump into this, what does this T here mean? Well, that T there stands for transpose. That is something we haven't learned yet. What this is it takes a given vector and it flips it over itself. So this 1, 2, 3 transpose is actually the column vector 1, 2, 3. I'm just writing it with this transpose notation so that it takes up less screen space. But whenever you see something like this, just think of it as a column vector, because that's what it actually is. All right, so is this vector a linear combination of these other two? Well, suppose it is. Well, what's that mean for us? That means there are constants, alpha and beta and r, such that alpha times -3, 3, -3, plus beta, 4, 2, 8, must equal 1, 2, 3. Okay, well, this is a vector equation if you stop and think about it. Every vector equation is actually equivalent to what? A system. So I can write this as a system. But we learned in, I don't remember what section it was, that a system is also equivalent to an augmented matrix. So what I'm going to do is actually convert this to an augmented matrix. And that augmented matrix is -3, 3, -3, 4, 2, 8, and then 1, 2, 3. Thinking back to that same section, what I must do now is row reduce this thing to the row echelon form, reduced row echelon form, and from there I can use the theorem that tells me about the consistency of a system and the number of solutions and such. So let's actually do that. The first step I want to do is eliminate both these entries using this -3 up here, and then also take that and negate the top row. So what I'm going to do is first E12 of 1, in other words, row 1 plus row 2 is stored in row 2, and then I need to do E13 of -1, which is -1 times top row plus the last row, and then lastly E1 of -1. And actually, for good measure, let's make that -1/3, because we know that entry needs to be a 1. Okay. Hit this row here with this row here with a 1/6, and this one with a 1/4. So what we're going to do is E2 1/6, E3 1/4. You probably noticed something already, but I'm not going to say what it is. And there, now you probably notice it. We have identical rows. So I'll do the second row plus the third row, the negative, turn it into the 0. And then I'll do 4/3 times this row plus top row. That's E21 of a positive 4/3. From here, we see that our alpha must be 1/3 and our beta must be 1/2. Let's actually check that. Let's see here. 1/3 and 1/2. So we have 1/3 of negative 3, 3, negative 3, plus 1/2 of 4, 2, 8. Does that equal 1, 2, 3? All right. This first one's going to be negative 1, 1, negative 1. Next one's going to be 2, 1, 4. Now, negative 1 plus 2 is 1. 1 plus 1 is 2. And negative 1 plus 4 is 3. So, yes, that worked out nicely. Wonderful. So, to answer the actual question, is the vector a linear combination of the other vectors? Yes, it is. Okay, next up, the span. So the span of a collection of vectors is a set of all linear combinations of those given vectors. This is a very interesting thing. All right, in the last slide, we asked if one vector v here was a linear combination of two vectors. What I was asking there is, in the same way, is v in the span of alpha, I'm sorry, not alpha, w and p? And we answered that the yes, because v is a linear combination of w and p. So that's one way you can interpret this. Another way you can interpret the span is it's the collection of all vectors I can reach with my given collection of vectors. All right. Let's do a really good example that kind of sets a tone for later on in the course. Let's call I hat, whatever I'm calling that, who knows, 1, 0, and j hat 0, 1. So when I visualize this in the plane, I hat is this vector of length 1 that ends at 1, 0, and j hat is this vector here that ends at 0, 1. Now the span of I hat and j hat what is that? What is the full collection of vectors I can reach using any possible linear combination of these two? All right, well, let's take an arbitrary vector in the plane. So let's take an arbitrary vector v, which is v1 and v2. Well, this vector v here, I can write it as a vector equation. How so? Well, that's going to be v1, 0 plus 0 v2, and that's nothing more than v1, 1, 0 plus v2, 0, 1. But what's 1, 0? 1, 0 is I hat, and 0, 1 is j hat. So what I've done here with this little decomposition is shown you that any vector v is indeed a linear combination of I hat and j hat. So in other words, given these two vectors, I hat and j hat, I can get to any vector in the plane. So therefore, the span must be the entire plane. So this is R2. All right, what is the span of I hat? Well, it's a set of all linear combinations of I hat. So this is equal to the set of all alpha I such that alpha is a real number. What is that? Well, that's nothing more than the x-axis, basically. What's the span of I hat plus j hat? I'll let you pause and think about that for a second here. Okay, so the first step is I hat plus j hat is this vector here. All possible linear combinations of that will span this line, which we can visualize as the line y equals x. So the span of I hat plus j hat is this line right here. All right. Now, in this example, I ask you, for what value of beta will this vector be in the span of those three? All right. Let's take a step back. If this vector is in the span of this collection of vectors, that means that it must be a linear combination of those vectors. So if it's a linear combination, that means there must be constants, alpha, beta, and gamma, such that alpha times that vector, beta times that vector, and gamma times that vector, when summed, will give me that particular vector. So that means I have alpha 1, -1, -2, plus beta 5, -4, -7, plus gamma -3, 1, 0 must equal -4, 3, and beta. Well, just like I did in that last example, I turn this vector equation into an augmented matrix. So that's 1, -1, -2, 5, -4, -7, -3, 1, 0, -4, 3, beta. And what I must do now is row reduce this thing. I will do this using magic. Magic meaning the pause button, and I do it all on the side and just put the answer down. So here we go. My answer is 1, 0, 7, 0, 0, 1, -2, 0, 0, 0, 0, 1. So that's my reduced row echelon form via magic. Now, of course, y'all can't use magic because you aren't a wizard like I am. But maybe you all become wizards and use my dark magic by the end of the course. But anyways, I digress. The last row here, it is telling us something very awesome, namely that 0 equals 1. Well, this is math telling us that what? There's never going to be constants alpha, beta, and gamma that will get us, oh my goodness, this is terribly confusing. I've used beta in 2 different contexts. Please forgive me. Oh my goodness, this is so embarrassing. This is beta prime and beta prime. There we go, all fixed. All right, anyways, there will never be constants alpha, beta prime, and gamma such that that linear combination will give me that particular vector. So in other words, no value of beta will suffice. So in other words, I will never be able to get a linear combination like I need to have one.